Welcome to the 13th lecture of EECE574, the graduate level probability and random processes. Homework 7 will be assigned, and midterm will be given as a take-home exam. I changed my mind because our progress in the covering is so slow. So the problems will be downloadable from next Tuesday noon, and you have around 2 days to submit your solutions. So the exam will cover up to class meeting 15. That will be the Tuesday's class meeting. Okay, here goes the overview. We are covering the last chapter of the undergraduate textbook we need. And it had some overlap with the chapter 7 of our graduate textbook. So we are actually beginning to cover the graduate material. Last time, we started to study chapter 5, which is entitled as the operations on multiple random variables. And this is divided into two. The first part is all about expected value of or expectation. Since we are now handling random vectors, we need to introduce the notion of the expected value of a random vector. And that is very simple to extend. But we started from two random variables case and introduced many interesting new definitions. So given jointly distributed two random variables and x and y, the first thing was so-called correlation. And we had this notation, capital R sub xy. And once we defined it, we have found some interesting cases where correlation becomes the product of means. When do we have it? In many cases, especially if two random variables are independent, then we always have this equality. However, on a side independence, we have some cases that satisfies this equality. So we define the term uncorrelatedness. And this name now, if you see something strange, what is uncorrelated? So this is correlation, and correlation becomes vectoring. So, okay, I try to understand that, but actually that is more related to the covariance. What was the covariance between two random variables and x and y? You subtract the means from the random variables, and then you compute the correlation. So if you keep this notation, you can even write it this way, x minus x bar times y minus y bar, right? So it's a correlation between the centered versions of the random variables. And this has relation like centered version is equal to uncentered version minus the product of the means. So we can reinterpret the uncorrelatedness as what? The covariance is 0, because this holds, then you have 0 here. So uncorrelatedness is misleading. It's kind of zero covarianceness, something like that. Got it? So uncorrelatedness now can be interpreted as zero covariance. We also had another definition of orthogonality. That means the expectation of the product x and y equals 0. And this is motivated by the geometric interpretation of the expectation of the product of two random variables. So we may view this expectation, this second order moment, as the inner product between the random variables x and y. In that case, inner product equals 0 can be said two vectors are orthogonal. So in this case, two random variables are orthogonal, we say it. And the reason why this means orthogonality will be more clear after we re-examine the mean squared error minimization. Anyway, so once we defined tons of correlation-related, second-order moment-related moments or expectations, we introduced something more that looks very interesting. So given two jointly distributed random variables, we may define the ratio of the covariance between x and y to the square root of the variance of x and variance of y, which means we have standard deviation multiplied, and we have the covariance between x and y. As this notation clearly shows you, the numerator has the unit of the product of the units of x and y, and this has unit of x and this has unit of y. So as I emphasized, the correlation coefficient is a unitless quantity. That is very important. And this can also be written as the standardized version of x divided by the standardized version of y. By the way, I will use many different notations to denote the same thing. For example, here, mu sub x is the mean of x, and also x bar will be used as the mean of x, as I wrote here. Okay. Sometimes I will use square bracket for the expectation. Sometimes I will use curly bracket for the expectation, even parentheses sometimes. Anyway, by definition, the correlation coefficient is simply the correlation between two standardized random variables. Interesting thing follows if we prove some lemma. The first thing is that we have this inequality. By the way, when we talk about correlation coefficient, as the definition says, we already assume that the two jointly distributed random variables have the first order means and the second order means. Okay? Because the moments may not exist given a random variable. For example, given a Cauchy random variable, it even does not have a mean value, even though the PDF is centered at the origin. Anyway, so under this assumption of the existence of the correlation coefficient, we can show this is true. And many proofs just show the conventional proof, just to show that consider this strange quadratic function of A that is always non-negative for all A real. So suddenly we have this inequality. We don't know the reason, and some proofs just say that, think about this. And since the left-hand side is a quadratic function of real variable A, we can apply the discriminant technique to show that this is true. You do it yourself. By the way, we are going to cover, because this is a graduate course, we are going to cover complex valued random variables too. In that case, we can similarly define the correlation coefficient, which is a complex number in that case. And I'm going to ask you probably in one of the homework problems to show something similar to it. And probably you'd better remember this approach or more fundamental reason why we use this strange quadratic form to prove this lemma. Anyway, the story behind is like this. Actually, we want to approximate y using a new random variable, capital Y, y hat, that is an affine function of x. Okay, suppose we want to approximate y by using x when x and y are correlated, which means that correlated means correlation coefficient is not 0. By the way, this means that here is another one. Uncorrelatedness means that this is 0, right? Correlation coefficient. So in general, correlation coefficient is not 0, which means that they have dependence actually. Correlated implies dependence always. Non-zero correlation coefficient. So this may be a good idea to approximate jointly distributed random variable y using x. Then the mean squared error, this is mean, and this is squared, and this is error. Mean squared error, when it is minimized over m and n, then what do we have? That is a question. And what we have is like this. The best affine approximation of a random variable y in terms of x is simply what? Is simply related to this inequality. Just a second. Yep. Am I correct? Yeah, I believe so. So be careful. Here I use y hat, okay, not y, because x and y may not always have a affine relation. However, as we try to find, y hat is an affine function, and actually this is the relation. So this minimization requires to minimize over n and m at the same time, but you can easily show that you can minimize n irrespective of the choice of m. And then you minimize over m. That is exactly the same as that one. Okay? You do it anyway. So this is the way to remember. Got it? So here, A is actually after you find the minimizing A becomes the correlation coefficient. Got it? Be careful. Here you have y and x. Here this is y, this is y and y hat. Be careful. Anyway, yeah, I believe I'm correct. Yeah. So this proof is motivated by this mean squared error minimization. And for what? A fine approximation of y in terms of x. Got it? Anyway, so we are interested in the case of the correlation coefficient equals -1, +1, and of course 0. And as you see here, what if the correlation coefficient is 0? What does that mean? What does that mean? Here, the value m is 0. So y hat is not a function of x when the correlation coefficient is 0. Got it? So you cannot find a good affine approximation. It's just a constant, right? Y hat equals some constant. That is the only good approximation when the correlation coefficient is 0. What about the case the correlation coefficient is positive? As you see, this is positive, that is positive and correlation coefficient itself is positive, means that your affine approximation has positive slope. If the correlation coefficient is negative, your affine approximation has negative slope. What about the case where rho equals 1 and rho equals negative 1? In that case, not only the slope has positive 1 and negative 1, actually this mean squared error, or you can say that mean squared error becomes 0. Okay? What does that mean? So here goes some lemma you have to remember. If you have the second moment of a random variable equals 0, if and only if x is 0 with probability 1. So this means x equals 0 with probability 1. Or you sometimes say that x equals 0 almost sure. Okay. So what does that mean? This is if you replace this one as some random variable, w, expectation of w square equals 0 when the correlation coefficient is plus or minus 1. Which means that if you really use that one, then what happens? Here, corollary means rho xy equals plus or minus 1, then y equals rho xy. Just a second. You have this equality almost surely. Got it? Because if you substitute a with rho xy, which is plus minus 1, then this equals 0 almost surely means that after rearrangement, you have that. Okay? And you will repeatedly see this form again and again and again. Okay? What does this mean? If the meaning of this equality becomes clearer when you draw a scatter plot. So you generate x and y at the same time. When correlation coefficient is 1 or negative 1, then what kind of scatter plot can you see? You see some points on a straight line. Okay. Okay. And by the way, this is called linear dependence. Okay, question.
여기서 correlation coefficient가 0이면 y가 x의 affine transformation으로 안 된다고 했는데.
No. It's an affine transformation, but the slope is 0.
x의 function.
It's still a function of x. It's like if you have a straight line y equals 0, that is a function of x, right? That is still a function of x. Anyway, so the last bullet says that if the correlation coefficient between two random variables is either 1 or negative 1, you have complete linear, actually affine dependence. So from x, you can deterministically know the realization of y and vice versa. The last topic of last class meeting was the characteristic function. And we introduced this notation. Here, x underscore means a random vector, and omega underscore is a vector valued variable of omega 1, omega 2, up to the length of random vector x. And this is defined as the expectation of e to the j omega vector transpose random vector x. Of course, you can expand the inner product between the two vectors using summation. Then due to the property of the exponent, you can just rewrite this as a product of e to the j something. And you can easily see that this is nothing but an n-dimensional Fourier transform. Of course, the sign is reversed, but you can just say that. And given that, we could do something interesting like this stuff. Okay, if the random variables are independent, then the joint characteristic function becomes the product of marginal characteristic functions, something like that. And what about the characteristic function of the summation of the random variables? And especially when those random variables are independent. Then as you know that the joint PDF is the convolution of these things. And as you learned in signal-gen systems, Fourier transform of convolution becomes the product of the Fourier transforms, right? That is called the product theorem or property. So as you see here, in this case, the summation of independent random variables, be careful here, the argument omega is scalar because you have a single dimensional random variable, right? The sum is just one length 1 vector, so omega. And as you see that you have the product of the characteristic functions, but with the same argument. Got it? So this case and that case looks very similar, but completely different. This is the joint characteristic function of independent random variables. So individual characteristic function has its own variable omega sub I, but this is the characteristic function of a single random variable y that is happen to be the summation of independent random variables. So you have the product of the characteristic functions evaluated at the same omega. Got it? Anyway, as the ordinary characteristic function, the joint characteristic function also gives you the moments and joint moments. Got it? After applying derivative and evaluated at 0 and divide by some j to the something. Anyway, that was the all about the characteristic function. We are going to move today section 5.3, but it seems that our undergraduate textbook omits very important topic related to the expectation. That is the conditional expectation. So I'm going to talk about it before we cover section 5.3. So the first topic is the definition of the conditional expectation, and that is actually not that difficult. So let's first define, given two jointly distributed random variables in x and y, we want to define so-called conditional expectation. But when we do some conditioning, what is given? A random variable is given or an event is given? An event is given. So we have to think about some event. And here we specifically consider a point condition. So suppose that we have observed some y0. Okay. Think about this source. Suppose I just hide the outcome from the upper branch and let you observe the output in the lower branch. And you have observed y0. Now I am asking, what would be the expectation of y given this event? That is the conditional expectation we are going to define. So this notation, expectation of random variable x and bar, there is the conditioning bar, and we put the event without using this event denoting curly bracket, that looks okay. We have been using the notations similar to that, right? And this is just very simple. What we need to do is to write it using an integral. For example, if we can find the conditional density, PDF of x, given the event, the point condition y equals y0, then this expectation is sigma, the integral of value times the PDF of x, given the event y equals y0, right? But we already have introduced a new notation like this, right? So the conditional expectation can be simply rewritten by using the conditional PDF of x given y. Very simple. By the way, we usually drop y0 because this holds for all y. So here I delete subscript 0, which is what you usually see from the textbook. Okay? So if we assume y as a variable, now what is this? This conditional expectation is a function of y. Okay? This is function of y. Am I correct? If y0 is y sub 0 is a constant, this is also constant, right, with y0. But if you regard y as a variable, then you have a function. Let's call it g of y. The reason why I'm talking about this is due to this strange notation. When I first saw this notation, I thought that I already knew this. But actually, it was something which I was not taught. See the notation carefully. Expectation of random variable x given random variable y. Something's seriously wrong, right? As I told you, whenever we talk about conditional something, we have condition in terms of an event. This is a variable. Then we have to define this notation, right? We cannot imagine what it could be. And actually, that is exactly the case is this. So suppose g of y equals expectation of x given capital Y equals lowercase y. Then this strange notation is defined as g of y. What does this mean? What does this mean? This is simply like this. Suppose you have, again, a source that generates two variables. And here you put G. Then what is the output? Whenever you derive a deterministic function using a random variable, what is the output? A random variable. This random variable could be denoted by G of capital Y, right? However, this G of Y is what? The conditional expectation of X given Y. And then we call this one as expectation of X given Y. So let me ask you a question. What is this one? It's a random variable, okay? Be careful. If when this function is G of Y and it is driven by Y, we have notation like what? Capital G of Y. However, if we stick to that notation, we have a strange notation like this. See that? If you just replace lowercase y with capital Y, you have this strange notation. Capital Y equals Y, right? That is why people do not use this strange note. They have introduced this strange notation. Got it? This is one of the most torturing notation when I was a graduate student. Anyway, so remember, conditional expectation of X given Y is a random variable. Conditional expectation of X given the event capital Y equals Y. What is that? It's a function of Y. Got it? This is a function of Y, and this, which I'm not going to use, is what? It's not used, but this new notation is used, and that is what? A random variable. So I believe I covered this one and definition. Okay, point condition. By the way, let's revisit our total expectation theorem. So when we study the expectation, we apply the total probability theorem to have the total expectation theorem. For example, you wanted to find the expected value of X. And this is hard to compute. Then what do? You introduce a partition of the sample space, and each partition is an event. So what you do is that you introduce some A sub n's, where union of A sub n becomes the sample space, and any two events are mutually exclusive. Empty set for m not equal to n. Then expected value of X is simply the conditional expectation times the probability. See that? This also gives us the consistent interpretation of expectation. Expectation of something equals the value times probability, right? So how can you interpret the right-hand side? Right-hand side is the average of the conditional expectations. So if the conditional expectations are averaged, then it becomes unconditional expectation. Now, given given two random variables n, x and y, I'm going to ask you how to compute the expectation of x using the conditional expectation of x given y. Okay, question. Which one? 여기? 이거는 n에 대해서 그냥 n이든 m이든 상관없고 어떤 파티션을 도입하는 거예요. So we introduce a partition of S. Okay. So in order to find the expectation, unconditional expectation of X, we introduce a partition of S such that union becomes the sample space and they are pairwise exclusive, disjoint. So what would be the new total expectation theorem? So same thing. What we do is that we consider this event for all different y. Okay? So the difference is this. Here we have what? At most, countably infinite events, right? So we have summation. Now let's consider a real valued random variable y. Then if y is a continuous random variable, how many events do we have? Uncountably infinite. One good thing is that the union of all these events becomes what? The sample space, right? And two different y's gives us what? The empty set. So actually, this event for all y, so some set like this, collection of events in the form of capital Y equals Y, and for all y in the real. What is this one? This is a partition, right? So this gives us partition. Now let's put it here. Means we want to do something like this. Now, as motivated by this our old friend, what do you want to do? Unconditional expectation equals the value times probability, now density. What is the variable here? Y. So density of y, dy, and you have the integral. And this may look strange, but actually, from the definition of the expectation of x, you can derive this one. Let me show you. And this is much easier, actually. As you remember, the leftmost hand side is what? Integral x times the PDF of x. Now, we introduce a trick. What is the density of x? How can you link this density using the joint density of x and y? Marginalization, right? So what we do is that we replace this part using integration of the joint density with respect to y. Am I right? Now you substitute this integral here, and then what do you want to do? You want to apply the chain rule. What is that? This is simply the unconditional density of y times the conditional density of x given y. And then you group x times the conditional density of x given y to have the conditional expectation of x given y. And then you have the marginal density of y and dy. That is this one. So you have this result. That's very interesting. Now let's combine this strange notation with this result. What do you want to do? Anybody? Anybody? So here goes the weirdest one. See that? Expectation of what? Am I right? Just replace this one with g of capital Y, g of y. Then it becomes obvious. Let's say this is g of y. Then what is that? Integration of g of y times density of y. What is our ordinary notation? Expectation of g of capital Y. Am I right? So expectation, this is simply expectation of g of capital Y. Then what is g of capital Y? G of capital Y is the random variable when you derive a deterministic function expectation of x given capital Y equals y. Now, what if you derive this function with random variable y? Here goes our notation. Got it? So it's like expectation, unconditional expectation of x equals expectation of x given y. Got it? So this is sometimes called nested or iterated expectation or iterated expectation. And sometimes just call it a total expectation theorem for two random variables. Got it? So you must be well acquainted with this notation. For example, I may give you something like this. Given three random variables, x, y, and z, rewrite this one using the conditional expectation of something given something. Got it? See that? This can be always rewritten as what? Given something, right? Because this is random variable. Let's say this is just z. Got it? And no, not g, because I said x, y, and z. Let's say that this is w. Okay, we call a random variable with a new name, right? You have x, y, and z. Then this is simply expectation. Confusing. Just a second. Just a second. No. This is totally wrong. Okay. I don't do that. I don't do that. Okay. You do it. Okay. Anyway, let me forget it. It's confusing, right? Really confusing. Anyway, so I believe we are done with the missing parts. Yeah. Just a second. So we've covered this one. And this part is actually covered already by this correlation coefficient related one, half of that. And I hope we have time to talk about mean squared error estimation. Okay, question. Okay. Of course. Yeah, of course you can have your PMF version of the iterated expectation. No problem. Okay, let's move on to section 5.3, jointly Gaussian random variables. And as our textbook shows progressively, we first consider two jointly distributed Gaussian random variables, x and y. And probably most of you have seen this equation already. It may look a little bit different, but actually the same. See that? The joint density of x and y when the correlation coefficient is not 1, neither 1 nor -1. Because here in the denominators, we have 1 minus rho squares. So rho cannot be plus minus 1. Got it? So here we have something similar like 1 over square root 2 pi times sigma squares, because you can rewrite this one as what? 1 over 2 pi sigma x squared times 1 over 2 pi sigma y squared times something, right? See that? You have square root 2 pi, that becomes 2 pi. You have sigma x, sigma y. Here, you have square root 1 minus rho squares. And also, here you have something strange, but it looks very similar to what? It looks very similar to x minus mu x squared divided by 2 times 1/2 x minus, y minus mu y divided by sigma y squared. The reason why we have similar form is that consider the case, extreme case of rho equals 0. Now, rho equals 0 means that this becomes the unity, right? And rho equals 0 means that this becomes just 1/2, 1/2, 1/2, and this cross term disappears, and you have your densities back. So first, if rho equals 0, then what? The joint density of two Gaussian random variables becomes the product of marginal densities for all x, y pairs. What does that mean? Independent. So in Gaussian case, uncorrelatedness implies independence for two random variables case. And of course, people have defined multiple random variables, jointly Gaussian distributed multiple random variables, to have almost the same idea. Of course, we haven't yet defined the uncorrelatedness of two random vectors. However, we can do that, as we will see in short. So here, x bar is expectation of x. Sometimes I will use mu sub x, mu sub y, sigma x squared, sigma y squared, and rho xy is just use the rho because we have only two random variables x and y. Of course, here is typo, capital X it should be, and it should be capital Y. By the way, this density function is called the bivariate Gaussian density. As I told you, some mathematicians love to call every random vector a random variable, but multivariate random variable if it involves more than two random variables. If it involves only two random variables, they call it a bivariate. Bi means two, variate means variable. So bivariate Gaussian density. And as you see from the form of the joint PDF, it's what? It's e to the negative something times the quadratic function of the standardized x and y, right? And as you remember from this law, this is always what? This is always non-negative. So, and also it touches 0 when x equals mean and y equals the mean of y. So as you see here, the joint density is upper bounded by the joint density evaluated at the mean of x, comma, mean of y. So you have a bell curve again. So in one dimension, the PDF of Gaussian looks like a bell curve. And you have the same thing. So in the two-dimensional space, you have the joint density that again has something like a bell curve. The difference is that sometimes it's level sets, in Korean, 등고선 or something that looks like ellipse, 타원. That's the difference. So if rho equals 0, that level sets are concentric circles. And if rho is not 0, then you have ellipses, concentric ellipses as level sets. What if rho is very, 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 very close to 1 or -1? The ellipse kind of shrinks to almost a straight line. So as we've seen, we have rho equals ±1 means linear dependence. You have the same linear dependence in joint Gaussian case. So this is the case where rho is positive and close to 1. Got it? As you see, this is the x-axis, that is the y-axis, and you have what? You have the scatter plot, right? And then you can find the two-dimensional histogram, and you approximate it by conditioning, considering the limiting case, and then you cut with some level, then the contour projected on the xy plane is called the level set. Okay, the level set is a subset of your domain, which is in this case r². So you have ellipse with this major axis with positive slope when rho is positive. Okay. As I told you, uncorrelated means independence in Gaussian case. By the way, there goes something interesting. So you can find the angle of the slope of this major axis of the slope. And now you may define a new axis, something like this. By the way, such a coordinate rotation or affine transform of coordinate can be done by an affine transformation. So you can always find some square matrix A, positive definite, the invertible square matrix A, and 2×1 vector B. And you can always find new variable x prime, comma y prime. And as you see from the Jacobi's method, what you have is that the new density function of two random variables x prime, comma y prime is what? Can be written as the original joint density of x and y. With some substitutions, you can find it from here, right? You subtract from left-hand side the b vector and multiply A inverse, then you can always find x in terms of x prime and y prime. and y in terms of x prime and y prime. Here, you must have x in terms of x prime and y prime, y in terms of y and x and y prime, and then here goes what? Your absolute value and determinant of this A. I already assumed A is invertible. By the way, why we have that one here? Probably you remember affine transform, y equals ax plus b in one-dimensional case, right? In that case, here goes the coefficient A that corresponds to this capital A. Same here. Anyway, so here, what do you have? If you remember this form, this is quadratic form, and you have affine transformation, then you still have quadratic form. What does that mean? You have the same form, now with different coefficients. And interestingly, you can show that after this coordinate transformation, so you use this data, which can be found like this, and you rotate the axis, and what happens? Very interesting thing happens. You have independence between x and y. In this case, your correlation coefficient becomes 0. Actually, that can be hinted from here. See that? What if from the beginning, rho was 0? Then this is 0, regardless of the variance or standard deviation of x and y, right? And what is the inverse tangent of 0? That is 0. Got it? So if the major axis has slope 0, then two Gaussian random variables are independent Gaussian random variables. Interesting also happens. You can easily show that the conditional density of two Gaussian random variables gives you always a Gaussian random variable. Here, what does this mean? If you fix y as y0, then you have some event. Then you have x Gaussian. So let's see from here. Consider some specific y0. Now you want to find the conditional PDF of x. What do? As I told you, you have a very narrow strip, and on this strip, you find the dots from your original 2D scatter plot. And then you plot a density. And interestingly, that is Gaussian. Why? Because this means that you substitute y equals y0 here. Now, what do you have? This is mere a constant. You take it out. This is a mere scaling factor. Then what do you have? You have a quadratic function of x. Then it's Gaussian after proper normalization, because your density, conditional density, must integrate to the unity. So conditional density is also Gaussian. Very interesting. What about the conditional mean? Here goes the shocking part. See that? Conditional expectation of x given y equals expectation of x, keep the unit of left-hand side and right-hand side. What is the unit of left-hand side? Unit of x, right? And you have a single term that is corrected or modified, x, and you have y minus expectation of y, that has the unit of y, but you divide by the covariance of y, which is actually variance of y. So now this unit becomes 1 over unit of y, but you have cross covariance that has the unit of x and y. So what is the unit of this term? Unit of x. But have you seen this already? Actually, yes. What is this? The right-hand side is the MMSE, approximation of y as an affine function of x. No, sorry. Is this the one? Yeah, I believe so. Yeah, MMSE approximation of x as an affine function of y. Before, we approximated y by using the affine function of x. Now here, this is approximation, affine approximation of x in terms of y. The role of x and y just switch it. Amazing, right? So in Gaussian case, that affine approximation is the same as the conditional mean of x given y. Very interesting. By the way, you can also find the conditional variance, the conditional covariance, and that is the covariance of x minus cross covariance divided by covariance of y times the cross covariance. So you have the same unit as x squared here. And this is also very interesting because in our previous derivation for the correlation coefficient, I already asked you to minimize the mean squared error. Actually, this becomes the mean squared error in Gaussian case. The covariance is the same as the mean squared error. So in many derivations of the of a fine approximation, sometimes people just assume joint Gaussianity. In that case, you just need to find conditional means and conditional covariances instead of finding the mean squared error and the minimized mean squared error. And then at last, you just say that, okay, actually, they were not jointly Gaussian. So what we've seen is the solution, something like that. Anyway, this is very important formula, and you will see it again and again and again in every estimation problems. By the way, here goes the definition of covariance matrix. And you haven't yet seen, but let me give you. So consider let's define the covariance between two vectors, covariance over vector x. And here, x has two components, x1 and x2. It's no longer x and y, got it? And this is defined as the expectation of x vector minus mu sub x vector. Now you know why I love mu sub something, because expectation has upper bar, then you have two bars, like something like this, and I really hate this. So I prefer that one. And again, you centerize and you take the transposition. This is the definition of the covariance matrix over random vector x. And since vector x has two components, x1 and x2, you can show easily that it is a 2 by 2 matrix that is simply x1, x1, cx1, cx2, cx2, x1, cx2, x2. Be careful. Each entry or element is the covariance of two random variables. And the left-hand side is the covariance of a random vector, 2 by 1 random vector. Now, we know what is this, sigma x1 squared, right? So we have sigma 1 squared. This is what? This is what? This is cross correlation times sigma x, sigma x1 and x2. So we have this, got it? And now, let me ask you, what is the determinant of this covariance matrix? From your no longer high school math, when I was a high school student, we learned 2 by 2 matrix inversion or determinant. And then you can easily see that it looks like something like what? Sigma 1, sigma 2. Yeah, something like this, right? So actually, 1 minus rho square comes from the determinant of this covariance matrix. And this shares you some idea about what will happen when we have more than 2 Gaussian random variables. So here goes n case. And in n random variables case, as you've seen already in your undergraduate course, they usually do not provide you the joint density because it's too complicated. However, you can be given, they provide in a vector matrix form. So here goes the joint density of a Gaussian random vector X. By the way, what is a Gaussian random vector? It's a random vector, and you know that. When we talk about random vector, what? Major theoretically, you have a single source, and you have multiple measurable functions, right? And then you eventually have a joint density or joint CDF. And given a random vector consisting of jointly distributed random variables, if their joint density is in this form, then this random vector is called a Gaussian random vector. Now let's take a look at the form of the joint density. It's some constant times e to the negative some positive part, non-negative part. So it's all again a bell curve in multiple dimension. In one dimension, it looks like a bell curve. In 2 dimensions, it looks like a bell hat, right? In n dimension, it looks like some bell hyper hat or something. Similarly, you have what? Variable minus the mean vector. Variable minus mean vector. And it's what? Transposition. And in the middle, you have the inverse of the covariance matrix. And what is the definition of covariance matrix? I've already told you. Here, expectation of x minus mu transpose. And each term can be shown this way. I've already done this for 2 by 2 case, right? So covariance matrix is an n by n positive semi-definite matrix in general. So what happens? Actually, this inverse may not always exist. Whenever you have inverse, be careful. Okay? This determinant may be 0. So actually, this is half complete description about joint Gaussian random variables. One good thing is that characteristic function and joint characteristic function always exist and fully characterizes random variables and vectors. So thinking about the joint characteristic function is much better, especially for Gaussian, because you see here, no inverse. Here you have covariance matrix, not the inverse of covariance matrix or covariance of matrix determinant in the denominator. You don't have something like that. So this is a better definition of a joint Gaussianity. And I really love this because we can also use this to use in our central limit theorem for a random vector. Got it? And we show that the characteristic function converges to this form. So let's see. First, suppose mean vector is 0 vector, then we don't have this one. So again, due to the duality of Gaussian function and its Fourier transform, they all, in the absolute value modulus, they all have bell shape. Same. See that if you just take the modulus, then this part becomes, because you have the product of e to the this one times e to the that one, and e to the that one, because you have j, you have modulus 1. So again, you have a negative 1/2 times some non-negative part. Again, the bell curve. So bell curve Fourier transformed becomes bell curve. One good thing is that you no longer have the inverse. Got it? And this one is similar to that term in your Fourier transform. For example, you have x of t whose Fourier transform is capital X of f. Now you delay x of t by tau. What happens? You have e to the negative j omega tau times the original Fourier transform, right? That is called the linear phase shift. Same thing. You have a linear phase shift by the mean. The difference is that since we reverse the sign in our definition of characteristic function, so we actually do not exactly do Fourier transform. Fourier transform reversed, right? So we have positive or plus sign here. Got it? Anyway, this one can be used for non-invertible covariance matrix case. By the way, in this case, X is called a degenerate Gaussian random vector because we have some impulse. Okay? As you remember, in two-dimensional case, if rho equals 1 or -1, what happens? Our scatter plot gives us a fine straight line, right? What does that mean? Two-dimensional density must have what? Impulse fence. Got it? Same thing in multidimensional case. Anyway, so using the joint characteristic function, the n-dimensional Gaussian random vector can best describe if the covariance matrix is invertible, then we have a joint density in that form. Please remember this one. So characteristic function is a much better approach. And now let's go back to our friendly n equals 2 case. Because as you see here, covariance matrix is a 2x2 matrix whose inverse is given by that one, right? You know how to invert the 2x2 matrix, right? And now you plug in to the general form, and eventually you have that uppermost two-dimensional Gaussian density here. Got it? So this is nothing but a special case of this general density function of Gaussian when n equals 2. Got it? Now there are some properties of n-dimensional Gaussian. In two-dimensional Gaussian, what did I tell you? When you consider conditional density of x given y, it was what? Gaussian. Same thing happens. Any joint conditioning gives you Gaussian density if all the involved random variables are jointly Gaussian. So here, any k-dimensional marginal density is Gaussian, any conditional density is the form of Gaussian, and something interesting goes here. Again, uncorrelatedness implies independence. But we defined uncorrelatedness among n random variables? No, between two random variables. So what's going on?
Dr. Joe, it is time to wrap.
Let's see this one. Here, in the covariance matrix of a Gaussian random vector, each term, not on this diagonal entry, but on the off-diagonal entry, can be written in this form: correlation coefficient times each standard deviation. Now suppose the entries are all pairwise uncorrelated. What does that mean? This is 0. What does that mean for the covariance matrix? All the off-diagonal entries are zeros. Now, what happens when you have off-diagonal entries are all zeros? Let's take a look at that. What is the determinant in that case? Product of diagonal entries. What is the inverse? inverse of the diagonal entries. Then your quadratic form can be factored into individual density functions. So your joint density factors into marginal densities. That's why here you have the interesting result. Uncorrelatedness means for all pairs of xi and xj, if rho ij equals 0 for not ij, then what? Independent. Got it? The last part is this one. Any linear transformation of a Gaussian random variable is also Gaussian random variable. This was very difficult when I was an undergraduate student, but now it can be very simply done, and I believe that is deferred to here. So let's defer that. And about the point conditioning, this is the last part. See that? Now, Z is Gaussian. And I just intentionally partitioned it into two, possibly of same length, but in general different lengths. Two vectors. Got it? I just named that. So it's like I have Z1, Z2, Z3, and cut it here, Z4, Z5. And I rename it X and Y. Got it? Given a Gaussian random vector Z. Now we have interesting things. By the way, correlation matrix, covariance matrix can be defined similarly to the correlation and covariance. And here goes the interesting thing. When Z is Gaussian, as I told you, conditional density is also Gaussian. Conditional mean is what? An affine function. Best affine approximation. Conditional covariance is the variance, a covariance matrix when you have the best affine approximation. The same thing when Z is a 2 by 1. In that case, you have only X variable and Y variable, and we've already seen, right? So the result with two Gaussian random variables case extends to two Gaussian random vectors like this. Okay, on this Thursday, we will cover this part. We have a long way to go, but since this is too important to spend just 1 or 2 minutes, I will talk about this one on Thursday. Linear transform of Gaussian random variable. Actually, generally, an affine transformation is Gaussian. Affine transformation of Gaussian random variables is a Gaussian random variable. Okay, that's all for today.